Hi, everybody. We'll be starting in just a minute or two.
Can we ask everyone to mute their microphones?
Okay, Tony, just let me know when you're ready.
Ready.
Okay, good afternoon. Welcome everybody to today's presentation on worker particulate exposure and heart disease, a case study on McIntyre powder. We have presenting today Andrew Zarnke from OHCOW and Sandra Dorman from CROSH. I just wanted to say a few words about how proud we are of Andrew and his work in this subject, which has earned him his PhD from Laurentian University. He started off with us when he was still very wet behind the ears, young student, and grew to play an exceptionally important role in our McIntyre powder project, of which he's now the frontline manager. And especially wanted to congratulate him on taking on this particular subject of heart disease, which, as many of you will know, has been somewhat dismissively put down to lifestyle factors by the health and safety system and the workers' compensation system in the past, despite the very intense exposures that people often suffer at work, and which have been known for some time to cause these conditions. And I think Andrew, the research from Andrew and Sandra goes a long way towards providing an example where the evidence of a particular exposure causing a meaningful increase in these conditions is very clearly demonstrated in a way that is going to make people sit up and take notice. So without further ado, I will hand it over to Sandra Dorman from CROSH.
Thanks, Dave. And thanks everybody for joining us today. I'm just going to share my PowerPoint slides. I'm happy to be here, and I'm happy to be talking about, well, it sounds terrible, but I'm happy to be talking about cardiovascular disease with you today in Heart Month. So just a quick review on me. I am the director of the Center for Research in Occupational Safety and Health here at Laurentian University in Sudbury. I did my training in physiology, pharmacology, with specialization in immunology, which is actually tied in pretty closely to the work that Andrew has been leading in McIntyre powder and cardiovascular disease in general. So I do teach pathophysiology at the university, and so I like talking about disease, even though it's depressing. It's always interesting. So hopefully I'll get you a little interested in disease. So I am talking about cardio and vascular diseases today, and I guess a couple of points that I just want to make before we dive in here is, as you're likely aware, cardiovascular diseases are the number 1, 2 battling it out with cancer for both morbidity and mortality in Canada and in most developed countries, honestly. And certainly there are genetic components to your risk factors around developing vascular disease or cardiovascular diseases. But absolutely other factors come into play. And so Andrew's going to be talking specifically about McIntyre powder, but it's not just McIntyre powder. And that's hopefully what I'm going to show you in my quick slides here. What I'm going to do is take you through basic physiology or pathophysiology of the common cardiovascular diseases, and then tie it into particulate exposure and as a hypothesis, I guess. And then Andrew's going to take you through McIntyre powder as an example of reality, basically, in the workplace. So I know McIntyre powder isn't something that workers are exposed to anymore, but there are lots of other particulates that workers are still exposed to that are contributing to cardiovascular disease. So hopefully by the end of my little lecture, you'll see why that is. Okay, so my first slide, I just want to walk you through sort of the major vascular disease progression. And so I've got three little pictures on the right-hand side. This first one says normal artery. And what you're looking at is like a cross section, and you're looking down the artery. And what you'll see is that it's pretty wide in diameter, right? So this is where your blood is pumping through to get to all your organs, delivering all that oxygen. And it's also, you know, what you would say slippery, because ideally you don't want things sticking to the inside of the artery or the veins walls, right? As we age, or if we're exposed to things in our environment that get into the blood, what can happen is you can get little tears in the blood vessel lining. And so that's what the second picture is showing you. And that does two things. One, it causes the, like where that whole vessel before was very slippery and actually resistant to anything sticking to it, it now has an area that is a patch where it's sticky, basically. And so now things can stick to that little tear. And related, your coagulation factors are going to get activated to try and like prevent any damage in there. So it's sticky, and it's also gathering platelets, basically. And then the third picture showing you the fatty plaque is kind of a highlight of the progression of what happens when you get a sticky spot on the vessels. Now things like fat that is going through your blood vessels, like normally, can land against the side of that vessel and start sticking to it. And the more it sticks, it's like a little island. It can spread out. And as it spreads out, it can actually go all the way around the vessel. It can go down the vessel. I'll show you actually, no, I guess that picture doesn't show it very well. But you can see that that's also creating an impact on the diameter of the vessel. So now I want to go over to the left-hand side of the page here, where we're talking about high blood pressure and atherosclerosis. And I've created this circular kind of event happening. So atherosclerosis, I should say, that's like the fancy terminology for getting fatty deposition on your blood vessels, okay? And these two things can happen in either direction. Like you could start with a tear from something and get atherosclerosis, which then is actually going to cause high blood pressure, right? And you can see that in this picture here with the fatty plaque, because the diameter of the vessel is a lot smaller, right? So if you think about your garden hose, if you just have the water pouring out of your garden hose, it comes out pretty floppy, right? It kind of flops out. It's low pressure. But if you put your thumb over the garden hose and you change the diameter of the garden hose, now all of a sudden the water starts spraying out at high blood pressure, right? That's what happens when you get fatty plaque buildup, is that the pressure, there's such a narrow space now for the blood to flow through that the blood goes through at a much higher pressure. So you can see how atherosclerosis causes high blood pressure, but high blood pressure also causes atherosclerosis. And the reason for that, I'm trying to show in this picture. So on the left-hand side, now we've got the same cross-section of the blood vessel, but you can actually see the blood in there. And so these big white fluffy things are what you call white blood cells, and the little ones are red blood cells. And they're shooting down, floating through the blood, right? But at high pressures, they can basically act like projectiles. So if I go back to my garden hose example, if I put a little bit of sand in the water that's coming out of my hose, at low pressure, the sand doesn't hurt and it would just fall out of the hose and fall onto the ground. But if I narrow the diameter and I increase the pressure, now that sand, like if you put your hand against it, would actually hurt, right? It would sting as it flew out at high speeds. And so the cells are kind of like little bits of sand in your blood vessels. So if you have high blood pressure, let's say from a genetic predisposition, you're also now going to create more atherosclerosis because those little cells are actually causing the tears in the blood vessels. And then you're building up fatty plaque, which worsens atherosclerosis. So this is kind of a negative cycle of self-supporting. And what's important here too is, I mean, when we think about atherosclerosis as a progression of disease, you can imagine that it progresses in two ways. On the one hand, an individual plaque can progress from, something very small to bigger, where it looks like this and it's occluding the whole vessel, right? But you can also think of progression of atherosclerosis within the whole body, right? Like I could have a fatty plaque developing in the artery in my arm, but I could also have fatty plaques developing in my legs or in my heart or in my brain, right? So atherosclerosis, the reason why I spend all this time talking about it is because atherosclerosis is the lead up to the develop of those more chronic cardiovascular diseases that are going to kill you, which we're going to talk about next. So starting with angina and myocardial infarction. So basically, angina is this little picture here, where you've got substantial fatty plaque buildup in a vessel that's narrowing the blood flow through that vessel. But the significance is that vessel exists in a heart vessel. And myocardial infarction is the extension of that, where actually the entire vessel becomes occluded, but that vessel is a vessel that's in the heart. So I'm going to show you a couple pictures to try and illustrate that. And I apologize, it looks like my middle animation here for the angina is not working. But what I've got three I'm trying to show you. So on the far left side, this is you're actually within the blood cell, and you can see that fatty plaque is not only extending around the entire vessel, like circularly, but it's also extending down the vessel, right? And of course, the middle picture is trying to restate that, highlighting that fact that as that plaque builds up, the blood flow coming down that vessel is going to get smaller and smaller. And then this X-ray over on the side, this is showing you an actual blood vessel. And so you can kind of see that the red arrows are showing you where the fatty plaque is. And so if the blood was moving down, let's say from the left to the right, you can see that the blood flow is really constricted where that plaque is. And so this is actually a picture of angina. And so this blood vessel is a blood vessel that's bringing blood to the muscle of the heart. And you can see why the muscle over here that's downstream from the fatty plaque, it's not getting as much oxygen. And now you can also kind of see what the symptoms of angina are, right? a person, in particular, if they try to go up a flight of stairs or anything basically that's going to make the heart start to work harder, the muscles are going to start moving more. The muscles are going to need oxygen to do that, but the ability for the blood vessels to deliver that oxygen to the heart muscle is impaired by the plaque, right? And so here's a picture of a heart, and it's actually showing you the blood vessels that feed the muscle. So you've probably seen this picture before, right? Here's your aorta, and we talk about the blood going out to the rest of the body. But the first blood that comes out of that aorta is blood that feeds the muscles of the heart. And so if you get angina at this little point that's illustrated here is number 1, all of the heart muscle shown in that gray black area below isn't going to get as much oxygen. And in this actual picture, it's showing you a heart attack where, so actually a clot has blocked, or the atherosclerosis itself has completely blocked now or obstructed that vessel. And now no blood, no oxygen is getting to the heart muscle downstream from that. And so you have a heart attack, right? Because the muscle is dying. Okay, hopefully that makes sense. I'm going to tie in one more piece, which is stroke in the brain. And basically, it's the exact same story that, except now when you're talking about what blood vessel is affected, you're talking about blood vessels in the brain. So here's a picture that illustrates stroke, where now the clot and the atherosclerosis has occurred in a blood vessel that's feeding a section of the brain. And when that happens, the blood can't get there anymore, and the neurons downstream are going to be in trouble. Okay, so that's sort of the pathophysiology of cardiovascular disease. The last thing I want to do is just tie in how this relates to particulate. And so, and this will link up to the McIntyre powder. So I've shown the illustration with McIntyre powder. So here's your little black particles. That's the McIntyre particles. You inhale that. The very small ones can get down into the deepest parts of your lungs, and they can initiate inflammation in the lungs. And inflammation, it's happening locally. It's causing damage here, but inflammation is a systemic response by nature. So I've tried to show you the zoom in. So this little circle is zoomed in this box on the right-hand side. And what it's showing you is that all the chemicals that are instigating inflammation in the lung are spilling out of the lungs and into the blood vessels. And in the blood vessels, what they do is they increase the coagulability of the blood and basically sets good conditions for a clot to form, and also sets good conditions for atherosclerosis to advance. Okay, so this is one of the reasons why you could see somebody, like you see this with firefighters. Actually, they go out, they fight a fire, they're exposed to smoke, and then 24 to 48 hours later, they have a heart attack. They have a heart attack because they had ongoing atherosclerosis already, but the inflammations that happened after the fire set the conditions to throw the clot, to induce the heart attack. The other piece, in terms of particulate exposure, is that very small particles are, so the little black squares, they are actually able to themselves cross out of the blood, out of the airways and into the blood vessels. So these little guys, they can directly cause tears now on the lining of the blood vessels. So I'm going to say that again. So they can directly cause tears on the lining of the blood vessels. So they're going to float around. They are, depending on where they get travel to in the body, they're going to cause new point starts for new atherosclerotic plaques. So this kind of exposure is also going to enhance progression of atherosclerosis, right? And so you can kind of see this combination of, and imagine too, if it's on a regular basis, we've got chronic inflammation happening and chronic damage to the vascular system that's contributing to cardiovascular disease. Okay, I do want to make sure that Andrew has lots more time for his, so I'm going to wrap it up. Small reactive particle matter can directly damage blood vessels, increasing inflammatory conditions, which are conducive to developing atherosclerosis, angina, heart attack, and stroke. And that's it for me. And after Andrew talks, we'll welcome questions from the audience. Sorry, Andrew, I'll stop sharing. Boop. I think I stopped sharing. Thanks.
Perfect. Thanks, Sandra. That was a perfect preamble to what I'm going to talk about. I'm going to try and share screen one. Can everybody see my slides?
Yep, just put it in slideshow.
I'm trying to. There we go. Was that good?
It's perfect.
Okay. I also just want to start off by just talking about how all of this work that I'm going to describe was conceived. It all was born out of a response to workers' voices, workers' concerns that have come to OCCOW. And I just want to say that, so as Dave mentioned, I help lead out a number of our large occupational disease cluster investigations at OCCOW. And there's many types of workplaces in Ontario where we see a large proportion of the diseases in those workplaces are related to cardiovascular disease. So it is a real issue now. And as Dave mentioned, it is probably the most under-recognized type of occupational illness. And as Dave mentioned, a lot of this was a major focus of my PhD research. And I'm just going to go through a bit of an outline. So I'm going to go through some of the history and background of McIntyre powder usage in Ontario. I'm going to talk a little bit about the potential for McIntyre powder to contribute to cardiovascular disease, and then talk about the incidence of cardiovascular disease in a cohort of mine workers exposed to McIntyre powder in Ontario. So in 1926, silicosis became a compensable occupational disease. There was very high rates of silicosis in Ontario gold and uranium mines at the time. And in order to track the health of workers, they created the mining master file. Each worker had their own miner's certificate, and it tracked information about periods of employment at specific mine sites, ore type, job title, whether they had McIntyre powder exposure, pre-employment medical exams, and annual chest x-ray results. And during this exact same time, in response to the same issue, they were developing McIntyre powder. The McIntyre Research Foundation was developing McIntyre powder as a prophylaxis or a preventative treatment to the effects of silica in the mine to try and reduce the occurrence of silicosis. So the official use of McIntyre powder began in December of 1943 at the McIntyre Porcupine Mine in Timmins, Ontario. And it continued until about 1980. This treatment in Ontario was mandatory to work in underground mines, gold and uranium mines, and in some surface jobs, like a mill operator type job. So the recommended dose from the McIntyre Research Foundation was 1 gram per 1,000 cubic feet of locker room air for 10 minutes. And this was based on the average mine worker would take about 10 minutes to get changed and get ready to go. So the idea was this would be dispersed into the space. The workers would be in there getting ready, and they would be inhaling it before they went underground. For some of the hygienists in the crowd, if you convert this down to a unit that we're more familiar with, it would equate to 35.3 milligrams per meter cubed for 10 minutes. And if we time weight that over 8 hours, it's 0.74 milligrams per meter cubed. And you can see an image there of the actual dust being expelled into the change room. And here's a schematic of the actual mine dry at the Porcupine mine. This specific mine dry was 80,000 cubic feet. So you would need 8 10-gram canisters of McIntyre powder to properly dose this space. You can see in each corner the aluminum blowers. So basically 1 canister at a time would take about a minute to expel. So it would take about 10 minutes for this whole process to properly dose this space for a single treatment before the workers went underground. This isn't a new thing, the idea of McIntyre powder contributing to cardiovascular disease. There was a previous study in 2013 by Peters et al., where they looked at Western Australia gold miners. They linked the miners' health records to the Western Australian Register of General's mortality database. And they had case definitions for cardiovascular disease, cerebrovascular disease, Alzheimer's disease, and pneumoconiosis, which would have included silicosis. They estimated standard mortality ratios by comparison to the general male population, as well as hazard ratios by comparison to the never exposed group. So that was an internal cohort internal comparison. So the first thing I want to point out is this red box, which, as I said before, includes silicosis. So if we look at, obviously, a large increase when compared to the general population for the whole cohort. But if we look at the never exposed mine workers here, you can see that there's a decrease. This isn't a statistically significant difference between these groups, obviously, but still, you can see that the never aluminum was lower than the full cohort, and the group exposed to McIntyre powder had an increase. And all we can really take away from this is that McIntyre powder did not reduce the occurrence of silicosis or mortality from pneumoconiosis as described in this study, which included silicosis. Now, if we look at the results for cardiovascular disease, we do see a larger mortality rate in the ever exposed to aluminum. And this is statistically significant, but there's no statistical difference between these two groups. So a limited amount of conclusion can be drawn from that. But if we look at the hazard ratio data, similar results, you can see that there is a kind of a borderline statistically significant increase here. But when they considered the aluminum dust exposure as a continuous variable, they did find a 2% increased rate of cardiovascular disease mortality for every year of exposure, and this was statistically significant. So what kind of biological mechanism could be going on here, and what other similar studies have looked at particulate exposure in cardiovascular disease? So there is a large body of literature around air pollution and particulate matter below 2.5 microns. And in 2018, the World Health Organization reported estimates of 7 million premature deaths caused by exposure to fine particulates. Fine particulates is another word for PM 2.5. And in 2019, Lelyveld et al. Reported estimates of 9 million deaths worldwide attributable to air pollution, with the strongest associations attributable to PM 2.5. So if we put that into perspective, we can also look at the World Health Organization's estimates for excess death rate from tobacco smoke at 7.2 million per year. So we can almost say that PM 2.5 exposure or fine particulate exposure is a larger risk factor for mortality than even smoking. So it's a large issue. This is just a summary of some of the landmark studies that have been done over the years, looking at PM 2.5 exposure and different health outcomes. The one thing I wanted to show here is just the robustness of the results for cardiopulmonary diseases. You can see a large increase in the relative risk of mortality from these conditions, but also just the how narrow the confidence intervals are. Like if you look at the results for lung cancer to the right, you can see a much wider confidence interval. So this is a very robust finding and association. So why is that important to McIntyre powder exposures? So McIntyre powder was a very, very fine aluminum dust. It was almost like printer toner, like that black soot is what it looked like. And there's been 2 previous studies characterizing the actual particulate of McIntyre powder, one by myself and colleagues in 2019, and one by David Verma in 2020. Both studies came to agreement on every one of the parameters, and they both found that McIntyre powder was 100% below 2.5 micrometers in diameter, and also 12% of the powder was below 100 nanometers or nanoparticulates. So Sandra covered well the vascular and the cardiac side of the physiology, but within the lung, when you inhale particles, larger particles, they have a higher probability of being filtered out in the nasal passages and the upper airways. So they don't penetrate as deep. Larger particle or smaller particles can be deposited in the upper airways, and if they're in the ciliated epithelium area, they can be removed within hours. Particles below 2.5 microns or PM 2.5 have a much higher probability to penetrate the lower airways or the alveoli. If you look at the diagram, you can see the little balls. That's the actual air sac where the oxygen is exchanged, exchange is happening, and it's a smooth epithelium. So there's no little hairs with a mucous membrane that kind of beat and act as a conveyor belt to help push particles out. So there's very limited particle clearance mechanisms in this part of the lung. And it can mean that something called lung overload can happen. So if you're being exposed to a very high concentration of particulates in a very short period of time, it can load up this area, it can overwhelm the clearance mechanisms, and it can make the clearance much, much slower. So in lung overload conditions, alveolar macrophages become overwhelmed with particles. So the picture on the right is an image of an alveolar macrophage, and they're basically a cell that would engulf a particulate and actually move it out. So it's a much slower process. So lung clearance would be greatly reduced or absent. Smaller particles can accelerate the process of lung overloading, and fine and ultrafine particles are much more easily translocated out of the lung into the circulatory system. So if we think back to Sandra's diagram, that's how the particles can get from inside the lung into the vasculature and travel into the heart and other areas of the body. And also lung overload can drastically increase this inflammatory spillover into the circulatory system and cause inflammation much easier. I also want to just highlight some other exposures in the mining environment that are linked to cardiovascular disease. So crystalline silica itself has been shown to increase the rate of cardiovascular disease, as well as heat stress, diesel engine particulate matter, nitrogenous byproducts from blasting, and just stress of a dangerous environment. These all can contribute to cardiovascular disease as well. So just in summation, the scientific evidence suggests that there's a dose-response relationship between particulate matter and cardiovascular disease. Smaller particles at high dose rates similar to McIntyre powder would favor lung overload conditions. lung overload conditions can increase the probability of particles being translocated out of the lung into the circulatory system. And this inhibited lung clearance mechanism would have likely enhanced the effects of subsequent dust and radon and silica and diesel exhaust experienced in the mining environment. So now I'm going to go over a cohort study that was a part of my PhD, where we looked at the incidence of cardiovascular disease in a cohort of mine workers exposed to McIntyre powder in Ontario. I also just want to point out Krosh, Laurentian, and OCRC were our major collaborators on this work. So the mine workers mining master file was identified and in the registered persons database to obtain Ontario health card numbers. The health card numbers allowed us to link the individual workers to Ontario health databases like the discharge abstract database, which were hospital visits, Ontario Health Insurance Plan claims database like physicians billing, and the National Ambulatory Care Reporting System, which were emergency room visits. We generated case definitions to identify cases of ischemic heart disease, which was a broader diagnostic category, which included many kind of atherosclerosis. It included myocardial infarction, congestive heart failure. So it was a very broader, more inclusive diagnostic category. And then we looked at myocardial infarction, which is a heart attack, and congestive heart failure, as well as stroke and transient ischemic attacks. I'm not going to be showing any of the data for the stroke. There was little to no results in the stroke category. So I'll just be focusing on the ischemic heart disease, heart attacks, and congestive heart failure. So I just wanted to show this to show you just how large this the group is. So there was 93,000 workers total in the mining master file. And you have to go through and kind of pare it down, find duplicate records. You have to make sure that people aren't passing away before the end of your follow-up period. And so by the time you get through that whole process, we ended up with study cohorts of about 25,800. And they were all very similar for each diagnostic category. We also used two exposure assessment protocols. So there was two different ways to identify McIntyre powder exposure in the mining master file. One was the self-reported McIntyre exposure from the annual medical exams. So this was basically like a yes, no checkbox on that card. The other way was to look at a known list of mines that used McIntyre powder for specific periods of time. So we've essentially used the workers' work history and where they worked as indicated on the card as a way to identify how long they worked at a mine that was using McIntyre powder. So here's some just summary results from the cohort, just to kind of show the difference between the self-reports and the historical reports, the different types of exposure assessment. You can see that there was more exposed workers identified using historical records. And then just to show you also the large number of, this would be our referent group for all of these analyses, is the never exposed mine workers from the mining master file. So here are the results for ischemic heart disease. So you can see the red line is just indicating the relative risk of 1. So anything above that would be, a greater than the referent group. And you can see for 1 to 5 years of exposure, we see statistically significant increase, a little bit over 10% increased risk, as well as in the 10 to 20 years. And then you see a big jump in the greater than 20 years for ischemic heart disease. And here's the results for myocardial infarctions or heart attacks. You can see as well here, the 1 to 5 year, we see about a 20% increased rate. And then when we go to 10 to 20 years, you see about a 30% increased rate. And then greater than 20 years, it jumps up to 50 to 60% increased rate of heart attack in the McIntyre exposed mine worker group. And for congestive heart failure, this one was a little bit more of a surprise. You see a very large increased rate at the greater than 20 years of almost 70% increase rate of congestive heart failure. So the 4-year survival rate of congestive heart failure is, I think, about 5%. So this is kind of showing, the severity of the type of heart disease. So to sum up the results, we found that the McIntyre exposed group compared to never exposed group had approximately a 10% increased rate of ischemic heart disease, myocardial infarction, and congestive heart failure. Mine workers with 10 to 20 years of MP exposure had about a 20 to 30% increased risk of heart attack and a 14 to 23% increased risk of congestive heart failure. In the greater than 20 years of McIntyre exposure, we saw a 50 to 60% increased risk of heart attack and a 60 to 70% increased rate of congestive heart failure. And all of the disease types appeared to be increasing with duration of exposure. So that's all the results and everything I wanted to talk about today, and I'd be happy to take any questions. I just want to acknowledge all the collaborators on this work and thank Sandra as my PhD supervisor for seeing this through with me, and OHCOW for taking on this work, as well as previous mentors, Dr. Douglas Borum at the Northern Ontario School of Medicine, and all the support from the OCRC to do this work. So thank you very much.
Oh, thank you, Andrew and Sandra. Do we have any questions? I didn't see anything in the chat. Oh, here we go. Here's one. From Douglas, how did your study account for confounding factors such as lifestyle factors?
Yeah, well, the study design itself was lended itself well to that, just simply that our referent group was also mine workers from Ontario that all would have similar lifestyles and other, especially exposures in the mining environment would somewhat be normalized across both exposed and non-exposed groups. One major confounding factor that is difficult to control for would be the association of silica exposure and McIntyre powder exposure. And there was some other results that we have that I didn't have time to show, but we did break down our analysis by ore type, and we're able to look at the differences between ever uranium mining, ever gold mining. And it was really interesting because in the gold mining group, the signal that we detected was conserved, and you could see that there was an increased rate of heart attack and congestive heart failure in that group. But when we looked at uranium mining, we did not see that same result at all. And it's interesting because in the gold mines in Ontario, actually the uranium mines in Ontario actually have twice the amount of silica in the ore. So typically, as a rule of thumb, we generally say your silica exposure is double that of a gold mine if you're working in a uranium mine. So that was kind of lent itself to us being a little bit more confident about what we saw was because of McIntyre powder. But obviously, that's a very, very hard thing to be 100% sure of in any kind of study like this. So I hope that answered your question. Sandra, I don't know if you have anything to add.
Okay, we have a comment and a question from Denny. Amazing presentation, Andrew. What are your thoughts about the synergistic effects of other risk factors? For example, stress from dangerous work conditions and McIntyre powder on CVDs. Got curious as you discussed the other risk factors on one of the slides. So, if you have anything to add to your last answer there.
Well, I mean, our study itself could not dive into those relationships, but just looking at the biological plausibility, I mean, when we think about synergy or additive effects, we typically want to see that the different exposures are contributing to the same mechanisms. And we can definitely say that, you know, just through what Sandra was describing and the effects of inflammation, if an exposure is triggering an inflammatory response, and that's the major instigator of the health effect, then we can say that there's probably at least an additive effect between the two different exposures. Synergistic is a little harder to do without studying in more depth.
We have a question from Eileen Duncan. Can we take from this that exposure to other PM 2.5 can cause similar health outcomes?
Sandra, do you want to?
Sure, I'll dive into that one. I mean, I think a real short way is kind of yes, but the complicated is it does matter what the particulate is to some degree, because different sources of particulate will have different reactivity in the airways. And so, I mean, when you bring in an external source, if it's very small, it can get down into the deepest parts of the lungs. There's sort of the upper area and the very low deep part, right? And your body still has to clear that no matter what. The upper area, it'll typically try and bring it back up and with a lot of mucus and you know, you'll see the dirt and spit, and although you may also swallow a lot of that, so it gets into your body in a different way. The very low level ones is going to be managed in a much more prolonged way. And so that's always going to be hard on the airways, and it's going to induce some level of inflammation. But some particles are going to be more reactive. So McIntyre powder, you know, Andrew did the study looking at the composition, and it's fairly reactive because, in part because it has the aluminum in it. Some of the other things that people are inhaling, like diesel particulate, you know, have carcinogens in them as well that are going to cause a lot of direct damage to the tissue and a lot of direct inflammation for that reason. So I'm going a little bit longer than, but basically I think you don't really want tons of particles in your lungs no matter what, but it does matter a bit what the particles are made of in terms of the negative outcomes.
Thank you.
If you wanted to add anything to that.
Yeah, well, I think just the particle size, I think, is a common thread throughout this, is just the nanoparticulates can get in there. The half-life of those particulates in the lung is much longer, and the opportunity for translocation. And as soon as it's in your bloodstream, it's going to be, you know, transported to any part of your body. So once it's deposited in a different organ, different tissue, that chemical structure is going to have different types of toxic effects dependent. So it's that translocation piece, I think, that's tied to the particle size that's really important to that question.
Okay, next we have a question from Donald Cole. Were you able to draw on other diagnostic information as covariates? For example, pneumoconiosis diagnoses, smoking, if MDs code it, etc.?
No, we didn't look at any other diagnoses. We didn't have any smoking data in the mining master file to link to, but we did consider that as a co-founder. I think the big one is the fact that we're not doing comparisons to the general population. I think we could generally say, just off the top of our heads, that mine workers might have a higher incidence of smoking. But from miners to mine workers, we can say that they're generally the same smoking history between the exposed and not exposed group. And also, we know that smoking history isn't going to be associated with McIntyre or correlated with McIntyre exposure specifically. So I think the effects of that confounding will be significantly mitigated in this type of study.
Thanks. Donald, did you have a follow-up? I don't know if you can just unmute yourself.
Yeah, just I was more thinking synergy than confounding,
Right.
given what we know about small particles and that kind of thing. The other piece that I was really wondering was, you pointed out what proportion were nanoparticles. And is there much literature around nanoparticles and cardiovascular disease?
Well, again, the bulk of the literature is around PM2.5, which would include nanoparticulates. Diesel, like the data for diesel particulates is, even more heavily weighted towards the nanoparticle size. But specific to nanoparticulates, there's not a lot out there, especially like workplace or in the kind of engineered nanoparticulates, there's more, but you'll see more of it, I'm sure, coming out.
Okay, from Douglas, how did your study account for potential differences in diagnosis of cardiovascular disease over time?
Well, I mean, we were able to control for age and birth year and things of that nature. Yeah, I'm not exactly sure what you are asking. Maybe age of diagnosis, if you're wondering if there would be any bias around age. But we were able to control for age, so I think a little, yeah.
I don't know if Douglas is able to comment. I took the question to mean sort of historically methods of diagnosis or conditions grouped into a particular diagnosis.
Well, the case definitions that we used were very robust. I mean, we were lucky that we had published validation studies showing all the different parameters and sensitivity to this type of administrative health data. I put the references in the slide there if you wanted to see that. But to have that is, adds a lot of weight to our ability to detect the different and assign different diagnosis to each worker.
Okay. Another question from, oh yeah, Douglas says, thank you, I should have used the word case definition.
Okay.
Donald asks, where is this study in the publication pipeline? Is it shareable, for example, with WSIB, Ministry of Labor, other stakeholders to flag the importance of work-linked CVD, not just among firefighters or in acute situations?
So yeah, we're in the process of submitting it to journals right now. There's no really other stakeholders involved in that part of it. But this webinar is trying to bring light to the results, and yeah, hopefully we'll be able to share the link to the published article soon.
Okay, thanks. And Val Wolf from our Hamilton Clinic has also shared in the chat a link to a webinar from last July on the hazards of environmental PM 2.5 in the form of wildfire smoke. Okay, do we have any other questions? All right, well, thank you so much, Andrew and Sandra. It was a very, very interesting presentation and some very important work.
Thanks for hosting and thanks for having me.
Yep, thanks for coming, everyone.
Thank you.
Have a good day.
Bye, everybody.
Thanks.